list of part B So just like in part A, every assignment which we did was having a common title, that is synthesize, simulate and download. So synthesis of main model, simulation of test bench model and downloading part which we could not do. And there we had used Xilinx synthesis tool for doing synthesis of main model, iSim integrated simulator for simulating the test bench, and Planide is to be used if you want to do pin locking, and ultimately for downloading the configuration file or programming file or bit file into an FPGA. So these three steps are expected from every assignment of part A, whether it is ALU, USR, FIFO or LCD FPGA interface. Similarly, we can frame a common statement for all the assignments to be done in part B, which is as follows. So we say here draw layout simulate observe the outputs, and last is analyze and conclude, right? So for every assignment of part B, we are supposed to draw a layout, simulate the layout, observe the different output waveforms, analyze the waveforms and draw some meaningful and technically relevant conclusions. So I will not write down draw layout every time. I'll just write the name of the assignment. So the first is CMOS inverter. In fact, it has parts actually. So I will not write something here. I will write something there afterwards. Okay. So as we know that CMOS inverter, NAND, NOR, and OR, all of them are combination systems. That is, although university has not mentioned this particular assignment with this title, we can give the title here combinational systems, or we can say combinational circuits. And the last bit under this assignment is actually half adder, that everywhere before that particular gate's name we have written CMOS, because you are expected to draw the layouts for these logic gates or different functionalities using CMOS logic family, right? So we have to draw the layout of a NOT gate, NAND, NOR, and or half adder, all using CMOS logic family. That is why I can write down here CMOS half adder. So as such, university expects us to draw the layout of CMOS half adder as a part of assignment number 1, but there is some problem there. Okay. Now the second assignment is 2:1 mux using TG logic. Okay, so TG actually stands for transmission gate logic. Now, when we actually analyze, now in the theory classes, we have started studying how to actually derive the transistor level schematic TLS from the given Boolean expression. So, okay, fine. First, let me write all 2:1 mux using transmission gate logic, and third is a 1-bit SRAM memory. Okay, so here some additions from my side are like this, that if we use the conventional approach for deriving the transistor level schematic of half adder, the transistor count goes something like this. So all of you know that half adder is a combination of one XOR gate and one AND gate. Okay, and we also know that XOR means it is A bar B OR with AB bar, and AND gate is A dot B. So from our theory concepts, I can actually derive that this particular XOR gate will actually take, now this A bar will take 2 MOSFETs, B bar will take 2 MOSFETs, OR gate will take 6 MOSFETs. There is a ANDing here, so again 6 and 6. So the XOR gate itself will take actually 18 plus 4, 22 MOSFETs. And again this particular AND gate will again take 6 MOSFETs. So according to our conventional approach, our half adder will actually take a total of 28 MOSFETs, which is very huge to be connected and seen on the laptop screen. Okay, that is what we do is that we use another approach which we will learn in assignment number 2. So now students understand one thing, that an alternate approach for implementing a CMOS half adder is not to go by the default Boolean expressions, but actually use an alternate approach. So alternate approach is something like this. So you implement one transmission gate, then you combine 2 transmission gates to obtain a 2:1 multiplexer, and then one such multiplexer you convert into an XOR gate, and second multiplexer you convert into AND gate. So in the theory sessions, we have taken one session how to convert multiplexer into logic gate. So using that concept of converting multiplexer into logic gate, first we are going to learn how to make one transmission gate, and then using 2 such transmission gates we will implement a 2:1 multiplexer. One such multiplexer will be converted into an XOR gate, and second such multiplexer converted into AND gate. So when I do this particular approach, then I find that I can actually implement a half adder using less than 10 MOSFETs. So you see there is so much saving in the transistor count. So we have achieved transistor count economy from 28 down to less than 10. That is why, because it is not possible to learn in the assignment number 1 how to use this alternate approach which we have just mentioned here. That is why we have to change the flow of assignments. So assignments flow will be like this. So 1, 2, 3, 4. After 4, we will learn how to make a transmission gate 5. Then we will learn how to make multiplexer 6, and then we will come here to the 7th point and we will come to 8 here, right? So the flow of assignments are 1, 2, 3, 4. Then 5th is we will learn how to make a transmission gate. Then from 5th we will use 2 such transmission gates to make a 2:1 multiplexer, and we are going to use 2 such multiplexers to actually make a half adder. So there will be a detour. So we will be performing assignments in this way. Okay, another important thing is, as such, apart from inverter, all other assignments involve only making the layout simulating and observing waveforms, but there is some kind of an analysis involved in inverter. So CMOS inverter is the simplest assignment to perform, but it is the lengthiest. What the point? So CMOS inverter is the simplest assignment to perform because it contains only one PMOS and one NMOS. Very simple layout. The layout actually can be made in less than 5 minutes. But there is a lot of analysis here. So what are the analysis involved is that as I told you in the agenda today, that assignment number 1.A will be taught by me today only itself. Right? So assignment number 1.A will be done by me itself. Why I said that it is the lengthiest? Because once you make the inverter, you are supposed to see the effect of changing the clock frequency, the load capacitance, and also the value of bias voltage VDD on the dynamic power dissipation. So it is the lengthiest. Now there is one more bifurcation in assignment number 3 is that if you remember the subject computer organization by Zaki Hemacher, I do not know if TE and TC students study this, but in that book the author has actually drawn the circuit diagram for a 1-bit static RAM memory cell. It is called as a 6T cell because it is made up of 6 MOSFETs. So there are 2 cross-coupled inverters. So one inverter takes 2 MOSFETs. So 2 cross-coupled inverters take 4 MOSFETs, and there is one NMOS switch on both the ends in the read and write line. So as such, that particular SRAM memory cell, it actually takes 6 transistors. So it is also called as a 6T cell, where T stands for transistor. So that particular author has implemented the 2 switches by using NMOS. So when I made the layout for that particular SRAM memory cell, I found that there is a problem. The problem is that because NMOS is used as a switch at both ends of the memory, that is why my output, whenever it has to be logic 1, I get a weak 1 at the output. So I get a strong 0, but I get a weak 1. So what I did is that I have modified that design by replacing the NMOS switch with a TG switch. So as said in the theory sessions, transmission gate logic is nothing but it is a sub-family under CMOS. So because transmission gate is basically a CMOS logic family, it actually gives us the merit of both strong 1 and strong 0. So when I replace the default design given in the book by replacing the NMOS switches with TG switches, the modified design gave me now both strong 1 and strong 0. That is why, although university does not specify that you have to use which kind of switches, but purposefully I have bifurcated this assignment as 1-bit SRAM cell using an NMOS switch. So students will observe how this design is having a problem, that it is giving a weak 1 at the output. And when the students replace the NMOS switches with a TG switch, then that problem is solved. That is why, in order to add more learning through SPPU assignments, we have made some bifurcations. Okay, so this is in brief the list of part B assignments which we are going to do before 5th of December. And I'm really telling you that this part B is actually a child's play if you actually know how to use the tool. So once you are at the correct starting point of part B assignments, then next part is very, very easy. When you see the demo, you'll understand that this tool is much simpler than our Xilinx ISA which we used in part A. So